Good afternoon, everybody. We are going to start with sampling distribution today. In order to get started with the sampling distribution, I will present you with an example. Okay, the example is this. Let's say you have 100 students in a class, 100 different students. And from that, you want to select groups of 30, not just 30 people, but groups of 30. Groups of possible 30 students, okay? 30. So that means you're going to select all the possible groups of 30 from a group of 100 students. How many different ways can this be done, you think? If you could please participate and let me know. So I'm trying to get all the groups of possible groups of 30 different students from a group of 100 students. So what is it you think? Danny says 3. Anybody else? 3. Lots of people are saying 3. That's good. Anybody else has anything other than 3? Anyone quickly? No? Okay. First of all, it's not how many groups I can select, how many different possible combinations of 30 that we can select. That's probably what the appropriate approach to the problem. So first off, I'm selecting groups of 30 students, but is the order important here? The answer is no. The order is not important. Order not important. Order not important. So if order is not important, this basically boils down to a combination problem. From a group of 100 different students, you're collecting groups of 30. So 100C 30, which comes out to be 100 factorial divided by 100 minus 30 factorial times 30 factorial. That's the formula. Remember, NCR, combination of R items from n distinct items, is n factorial divided by n minus R factorial times R factorial. That's exactly what I'm using. So that comes out to 100 factorial over 70 factorial, which is 100 minus 30 times 30 factorial. And this number, by the way, there is an exact number which is too long, so I'm kind of approximating it, is 2.9 times 10 to the power 25. How big is this number? Let's say extremely big. For the practical purposes, this is infinity, okay? For the purpose of our practical example, this is literally infinity, because so many groups of 30 you can pick from a group of 100. All of these groups are, so all these groups that you're getting, they're different. They have at least one item different. So the point of this exercise is this. 100 is not a big number, right? If you have a population of 100 people or 100 items, that's really rather quite small. And if you select 30 possible groups of 30 from this 100, and it comes out to be humongous number. Now imagine when your population is even much bigger. It's easy to have population in the millions, okay? Or in the tens of thousands or hundreds of thousands of items in the population. It's not unlikely. In that case, how many ways can you do this or something like this? That's probably even bigger than this. So moral of the story is this. If you are selecting items from a population, you have many, many ways of doing it. Many, many ways of doing it. Now, for this simple example, think you have just only 100 items in the population, and there are 2.9 times 10 to the power 25 different ways of you picking groups of 30. So let's say I label them by group 1, group 2. So my first group, let's say group 1, for that group, I pick 30 people, and I get an average for that group, x1 bar, okay? And I leave it there. For my group 2, again, I pick another 30 people and find some average for them, okay? Whatever it is I'm measuring, I'm finding the average. For group 3, I'm doing the same thing, 30, x3, and I keep going down, keep going down, keep going down. And my last group is gonna be G2 times, 2.9 times 2.9 times 10 to the power 24. And the last group will have also 30 people in it, and that will have a mean as well, is gonna be X sub 2.9 times 10 to the power 25. It's not 24, 25. Okay, and you can imagine how many possible groups of, how many possible different X sub I bars you're getting. These are all the collection of X sub I bars. That means averages of each of these individual groups, okay? Averages of each of these individual groups. Now, if you take this billion, no, it's not billion, it's not even trillion, way, way more than trillions of averages, and you graph them, you're gonna get a graph like this, bell-shaped. You're gonna get a distribution, and that distribution of these averages, of all the possible averages of sample size n is equal to 30. Look, all of these groups that you created, each of them has 30 items in it, or 30 students in this particular case. So of all the possible groups of 30 students from this group of 100 students, you get average for each of these groups. And that average, if you, those averages, if you graph them, it looks like this. And this is, by the way, called the sampling distribution. Sampling distribution. What is sampling distribution? Sampling distribution is the distribution of sample averages or sample mean. Look, each of these is a sample average. Each of these is a sample average. Each of these is a sample average or sample mean. So sampling distribution is the distribution of sample means. Sample means or averages, right? For a particular sample size. Okay, in our case, that particular sample size is n is equal to 30. So that is what we say when we say the sampling distribution. Okay, is the distribution of all the sample averages. Now, remember, there is a little bit of observation here. When your sample size n, okay, n is greater than 1, that's when you're dealing with sampling distribution. Sampling distribution, not standard deviation, sampling distribution. When your sample size is greater than 1, that's when you're dealing with sampling distribution. But if your sample size is exactly 1, then you're actually looking for population distribution. You're looking at population distribution. All right. When your sample size is 1, you're looking at population distribution. So this is what a sampling distribution is. A sampling distribution is the distribution or the shape or graph of all the possible samples that you can get from a population with a particular sample size, okay? With a particular sample size. Now, I have selected n is equal to 30. You could have selected n is equal to 29 if you wanted, that's fine. You could have selected n is equal to 30 if you wanted. You could have selected n is equal to 31. Anything is possible from all the way down from 1 to up to 100, right? Because our sample, hypothetical sample, has 100 students. That's my population. I meant to say population. Our hypothetical population has 100 students. So your sample size could be as low as 1. In that case, you are getting the population distribution, and as high as n is equal to 100. In that case, you just get a single point, right? You have the entire population. And these are two extreme values, but in between, you can pick any other values. Is this clear, everybody? Any question on the sampling distribution?
No.
Okay. Now, let's go ahead and look at the definition a little bit closely. There are a couple of things that I talk about here. Oh, by the way, the actual number is this. So this is the actual number. How many different ways can you select groups of 30 from a group of 100 distinct items? That's the actual number. If you write it out, it's approximately 2.9. So look at these first two numbers, 2.9 times 10 to the power 25 different ways. This is crazy big number. Literally, it's infinity for practical purposes, as I said. Now, let's go ahead and elaborate a little bit more on sampling distribution definition. Sampling distribution is the distribution of the sample means for a particular sample size. Sampling distribution is the distribution of sample means for a particular sample size, okay? Now, I kind of gave a more of a narrow definition in the first case. So I kind of want to elaborate on this. Here I said means, okay? Sample mean is a statistic, not statistics. It's a statistic, some property of the sample. Now, this does not necessarily have to be sample mean. It could actually be a proportion too. We have corresponding or equivalent definition of sampling distribution for proportion. So I replace this. So sampling distribution, I replace the sample mean by sample statistic, okay? Just to make it broader. The sampling distribution of a sample statistic is the distribution of all possible sample statistics, okay, of that particular sample size. Here, the statistics is not the subject itself, is the plural of statistic, which is a characteristic or property of a sample. Now, when you're dealing with sample size of 1, which I already said, you're dealing with the population distribution. When sample size is greater than 1, we are dealing with the sampling distribution that we discuss here. So we are dealing with sampling distribution versus population distribution. And then when your sample size is bigger than 1, that's when you're dealing with sampling distribution. When your sample size is exactly equal to 1, you're dealing with population distribution. So please keep that in mind, okay? So just to summarize things, sampling distribution is the distribution of the sample means for a particular sample size, which is this. Also, we could generalize it to sampling distribution is the distribution of sample statistic. Okay, sample statistic for all the possible sample statistics of that particular sample size. Okay, so this word in essence include things other than mean. It could be proportion, it could be standard deviation, things like that. Now, if the sample size is 1, then you're dealing with the actual population distribution. If sample size is bigger than 1, then you're dealing with sampling distribution. Now, to get a sort of like hands-on example or hands-on experience with this, I'm gonna give you a very naive and simple example. Very naive and simple example, and I want you to try that example, everybody. Let's think of a very interesting population, okay? I have a very interesting population. The population contains 3 numbers, 1, 2, and 3, in the traditional sense of numbers. That's all my population is. And this population must have a mean. Population mean is mu, and it also has a population standard deviation sigma, whatever it may be, okay? So my numbers are 1, 2, and 3. Now, that's my population size. That means I have 3 items in the population. Now I want you to do a couple of things. Find this mu. That means population mean. Remember, I told you it will be very important for you to know what is the difference between mu and x bar. Mu is the mean of the population, whereas x bar is the mean of the sample. I said it many, many times throughout the semester. The difference between mu and x bar. Then difference between sigma and s. Sigma is the standard deviation for population, and s is the standard deviation for sample. Then p is the proportion for population, okay? And p hat is the proportion for sample. So these are the things that you want to be clear about in terms of idea, okay? Now I want you to go ahead and find the mu for this, which should be very easy. That means average. Then from this group of 3 items, from this population of 3 items, select 2 items, okay? And for each of these items, whatever many ways you can select, you find the x bar, okay? Or x sub I in this particular case. Whatever number of groups of 2 you can collect from these 3 distinct items, you get the average for each of these groups. The first group, you call it x1 bar. For second group, you call it x2 bar, and so on and so forth. So I want you to spend a few minutes working on this, and then I'm gonna come back on the screen here, and I'm gonna do it for you, and you will see exactly what I mean. This is a very, very simple example so that you can get a hands-on experience with your with sampling distribution and the sample means. Yes, someone had a question or anything comment? Okay, so go ahead and spend a few minutes, please. Okay, guys, so what is the number that you got for mu? What number do you have for mu? What's the average of these 3 numbers? The average of 1, 2, 3, you don't know? The average of 1, 2, 3 is what? 1 plus 2 plus 3 divided by 3 is equal to 6 over 3 is equal to 2. So the population average is 2. Now, how many different ways can you pick 2 items from a group of 3, which is very easy. 3C2, which is 3 factorial divided by 3 minus 2 factorial times 2 factorial, which is equal to 3 factorial over 3 minus 2 is 1 factorial, 2 factorial. So there's going to be 3 times 2 factorial divided by 2 factorial, which is 3. So that means you can pick 3 groups of 2, which is very easy to identify. That's why I gave you this problem. So the first group is 1, 2, and the average of that is going to be 1 plus 2 divided by 2, which is 1.5, and I call it x1. The second group is 2, 3. So 2 plus 3 over 2 is equal to 2.5 is equal to x2. Third group is 3 and 1, which is 3 plus 1 divided by 2 is equal to 2, which is x3. So all of these, x1, x2, x3, are all the possible ways you can collect. I mean, this one, and this one are all the possible ways that you could collect 2 items from a group of 3. So for the first group, your sample statistic is x1. For the second group, your sample statistic is x2. For the third group, your sample statistic is x3, right? Now the distribution of all these 3 averages would be called sampling distribution. The distribution of all of these 3 averages is called sampling distribution. Obviously, I made it very simple and sort of naive, extra simple example, just to get the concept through your head. But in reality, this will be in the billions, trillions, whatever, okay? If you're dealing with real world example. And if you take all of these averages and you graph them, you should get something that looks like bell shaped with certain conditions. So we'll talk about them later. Now, I kind of want to lead you to a new idea right now, okay? I want you guys to go ahead and find the average of these averages, okay? So these are individual averages for each of these groups. So sorry, I meant to say not x1. I meant to say x1 bar, x2 bar, and x3 bar, okay? Okay, so that's the sample average. So these are 3 sample averages, right? Now, go ahead and find the average of these averages. That means mean of these means. So if you do that, it boils down to x1 bar plus x2 bar plus x3 bar, all of it divided by 3. If you do the math, you're going to get 1.5 plus 2.5 plus 2, all of it divided by 3, which, by the way, is 6 divided by 3, that is 2. So the average of these possible different averages, or average of these averages, is 2. Now, if you go back and look at your population average, which is also 2, and this average of the averages is also 2. Now, is it a coincidence that it happened for this particular case, or is it more of a general trend? As it turns out that it is not a coincidence. It didn't happen by chance or by luck. It is actually the case. So the population mean, the mean of the population or the average of the population is actually the same as the average of the averages, which is the average of the sampling distribution or mean of the sampling distribution. That's exactly what we see here. And this mean has a special symbol for it. We use mu for this mean as well, but with a subscript x bar, mu sub x bar. This symbol, whenever you see, you should be thinking of sampling distribution. Whenever you see this, you should think that you're dealing with sampling distribution. You're dealing with sampling distribution. Okay, so one of the conclusions of central limit theorem is this. Number one, conclusion number one, mu sub x bar, that means mean of the sampling distribution, is the same as the mean of the population with certain restrictions. And that restriction, we'll talk about it more when your sample size is bigger than or equal to 30. When your sample size is bigger than or equal to 30, okay, the mean of the sampling distribution is the same as the mean of the population. Remember, you get different sampling distribution for different sample size. So if n is greater than 1, you're dealing with the distribution of the, sampling distribution. If your n is equal to 1, you're dealing with the population distribution. So make sure that you're clear on this. Now, that's one conclusion. And there is a second conclusion, which is this. These numbers have a standard deviation. So does these numbers. Okay? These numbers have a standard deviation, whatever it is, and we call it sigma. All right? And these averages, the distribution of these averages, they also have a standard deviation, and we call it obviously and naturally sigma sub x bar. Okay, like the mu sub x bar, we call it sigma sub x bar. That means sigma sub x bar tells you the standard deviation of the samples. Okay, standard deviation of the sampling distribution. Okay, now there is a relationship between this sigma sub x bar and this sigma. And that relation, by the way, is sigma sub x bar is equal to sigma divided by square root of the sample size. That means how big is your sample? If n is bigger than 1, let's say if it is 30, you will divide it by 30, square root, of course. If it is 100, you divide it by the square root of 100, and so on and so forth. So these two are called the conclusions of central limit theorem, given that your sample size n is bigger than or equal to 30. Okay? If your sample size is bigger than or equal to 30, then mu sub x bar is equal to mu and sigma sub x bar is equal to sigma. In addition, there is another thing you can assume, that the sampling distribution is bell-shaped. Technically, this should be the first thing, but the way it worked out here, this came first for me. Okay, so this is the sampling distribution, not standard deviation, sampling distribution. The sampling distribution of the sample means is bell-shaped or normal or Gaussian, and the average mu sub x bar is actually equal to mu. That means the population distribution. If the population is distributed like this, I don't know, maybe not. Let's make it some. If the population is distributed like this, some arbitrary distribution we don't know, that's your mu and your sigma. If your sample size n is greater than or equal to 30, then distribution of the sample means or sampling distribution will be bell-shaped. Does not matter what the shape of the original population is. It could be anything. It could be anything, the original population. Remember, in this distribution, sample size is 1. In this distribution, sample size is greater than 1. In particular, we are talking about n is greater than or equal to 30, and then we will bring it below 30 with certain conditions. Okay, so let's, for the sake of argument for now, let's assume that sample size is greater than or equal to 30. And this one is the population distribution and sample size 1. Now, what you want to do is this. Pay closer attention. At first, when I learned this thing, this conclusion, I was really amazed. My goodness, it's crazy. Why is it crazy? Doesn't matter what weird shape you could have for the population. But if you make your sample size bigger than or equal to 30, sampling distribution is always bell-shaped. Sampling distribution is always bell-shaped with a mean of mu. Okay, mu sub x bar is mu, which means the mean of this sampling distribution is the same as the mean of the population, which is this. And standard deviation sigma sub x bar is sigma over square root of n, which is this. And this gives you a lot of power. I mean, tremendous power. This is the heart and soul of kind of statistics, you can think of it. Many of the things that we do in statistics are based off of this, what we call central limit theorem, CLT, central limit theorem. It's so important to the study of statistics. It has been given a special name, central limit theorem, I guess, is central to all the things that we do in statistics. It is called central limit theorem, and the conclusions are these two conclusions. Mu sub x bar, that means mean of the sampling distribution, is the same as the mean of the population. And sigma sub x bar, that means standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of the sample size, which is square root of n. Any question, anybody? Anyone has anything, any points to add? No questions. All right, so let's move on. So my central limit theorem, CLT, if version 1, version A, let's call it, if n is greater than or equal to 30, it doesn't matter, okay? It doesn't matter what the distribution of the original population, sample size n is equal to 1. And this is the population distribution, okay? Let's say with a mean of mu and standard deviation of sigma, right? It doesn't matter what it is. The sampling distribution is always going to be bell-shaped. Sampling distribution is always going to be bell-shaped with mu sub x bar being equal to mu, that means the population distribution, and sigma sub x bar is sigma over square root of the sample size, which is n in this particular case greater than or equal to 30. So this is a very powerful conclusion, very, very powerful. Make sure that you understand it. Now the version 2 is, what if n is less than 30? In that case, what do you do? Oh, okay, let me write down the conclusions. Even though I wrote it down here, I'm going to write it down here again. Mu sub x bar is equal to mu. And number 2 conclusion is sigma sub x bar is equal to sigma over square root of n. Sigma sub x bar is equal to sigma over square root of n, where n is the sample size. Okay. Now, what if n is less than 30? In that case, how does it work out? These two conclusions still holds true, okay? One is mu sub x bar is equal to mu. Number 2, sigma sub x bar is equal to sigma over square root of n. These two still holds true only if the initial population, which is this population, only if initial population is bell-shaped. If you are drawing your sample, okay, like here I'm drawing my sample of size less than, greater than or equal to 30 from this population, okay? But if your sample size is less than 30 and you draw from a distribution of a population that is bell-shaped, in that case, these two conditions are going to still hold true, and the sampling distribution is still going to be bell-shaped, which is mu sub x bar is equal to mu, and sigma sub x bar is equal to sigma divided by square root of the sample size. So this one has a mu and sigma standard deviation. So bottom line is that if sample size is less than 30, your initial population that you are drawing your samples from must be bell-shaped. Then both of these conditions will be satisfied. But if you do not know that initial population is bell-shaped, then for sample size less than 30, you could not conclude these two. You could not conclude these two. But if your sample size is bigger than or equal to 30, doesn't matter. Regardless of the distribution of the population, the sampling distribution is always going to be bell-shaped. And that is a very, very, very powerful tool. It lets us, make conclusions about distributions, population distributions, and population properties that we have no clue about. Okay, we don't know what the shape is like. It could be some arbitrary shape. It could be normal or bell-shaped or Gaussian distribution, or it could be any shape. Doesn't matter, any arbitrary shape. But this sample size of greater than or equal to 30 ensures the normality condition here. Okay, that means it is a normal distribution, and these two conclusions hold. That gives us a lot of power to make conclusions or make predictions about the original population. This is not the original population. Original population is this guy and this guy, right? These are just sort of like derivative. We created another distribution by sampling these two populations. Okay, is it going over your head? Are you okay?
Yeah, so far.
So far, okay? All right. So now let's go ahead and do problems. The best way to learn something is doing problems. So let's do the central limit theorem. I already talked about it. Central limit theorem example 1. So the first example is Mr. Zuckerberg example. Many years ago, more than a decade ago, I think, he said that people spend about 50 minutes per day on social media, such as Facebook, Instagram, and Messenger. I just was asking my other class earlier in the day. This number has gone up, I'm very sure. It's not 50 minutes anymore. I think people spend more than that on social media nowadays. And of course, Facebook, Instagram, and Messenger are not the only social media right now. There are many other social media. Okay, so now he claimed that on the average, a person spends about 50 minutes per day on social media. And the standard deviation is 30 minutes. And also, we are assuming that the time spent on social media is normally distributed, means it is bell-shaped. So the original population is bell-shaped. Here, the original population is bell-shaped. So let's go ahead and do this problem. So let me sketch something for your convenience. Thus, the original population is bell-shaped with a mean mu is equal to 50, and standard deviation sigma is actually 30, let's say. This is for sample size of 1, remember. So first question is this: what is the average number of minutes that a person spends on these social media channels? Note that the sample size is 1. That means, which is given here, which is what? Mu is equal to 50. Sure. What is the standard deviation for the distribution with sample size 1? That means, again, we are asking about the standard deviation of the population, which is given to be 30. So these are pretty straightforward and easy. Now, let's go ahead and do rest of the problems here. Okay. Now, if you now take a sample of 25 people, okay, from this population. Now your n is 25. Pay attention. Your n is equal to 25. You took a sample of 25 people who use social media, then what is the average of the sampling distribution? What is the average of the sampling distribution with sample size n is equal to 25? Now, first of all, what is the shape of the sampling distribution? Can you tell me, you guys? What is the shape of the sampling distribution? How does it look like? The shape of the sampling distribution. What is the shape of the sampling distribution? Anybody?
Bell shape.
It is bell-shaped. Why? Even though n is less than 30, you are correct. It is bell-shaped. But can you elaborate why it is bell-shaped?
No, I cannot.
Anybody else? Who is Abimael Solas? Who's this person? Abimael, did I pronounce your name properly?
Yeah, it's fine. Yeah.
I haven't seen you in the class before, looks like.
Yeah, I've been a professor.
You've been here? Okay.
Yeah, every single time. Yes, sir.
How can I miss so obviously?
I don't know.
Okay, all right. What do you say? Anything, any comment on this? Why is it bell-shaped, the sampling distribution? Even the sample size is less than 30.
Honestly, Professor, I'm not sure.
Okay. Anybody else? Ashley Miranda? Ashley Miranda? Pedro Alvarez? Pedro Alvarez?
Yeah, I'm here.
You know why it's bell-shaped?
No, I don't know.
All right. So look, I'm taking a sample of size 25 from where? From here, right? So from this population, what is the shape of this population or distribution of this population is bell-shaped, right? So remember, if you are drawing from bell shape, it really doesn't matter. It really doesn't matter whether sample size is 30 or less. It's inconsequential, okay? So that's why it is bell-shaped, even though the sample size is less than 30. So now what is mu sub x bar? Remember from the conclusions of central limit theorem is that mu sub x bar is equal to mu, but mu is 50. So it must be the case mu sub x bar is 50. That means mean of this sampling distribution is 50. Now the next question I'd like to ask is sigma sub x bar. What is the value of sigma sub x bar? That means what is the value of the standard deviation for the sampling distribution? Now remember, there is a relation between standard deviation of the sampling distribution and standard deviation of the population. So I want you to go ahead and tell me what this value is. I want volunteer, try it. Okay, volunteer please, otherwise I will volunteer you. It's okay to make mistakes, but it's not okay to be quiet and not be participating. Alondra Juarez. Alondra Juarez. No Alondra here. George Lopez. George. I can't hear you. I think you're trying to talk or somebody's trying to talk. I can't hear you. Okay, Pedro Alvarez. Pedro,
Hello.
yes.
Isn't it what was it?
Sigma sub x bar. That's what I'm looking for.
Wasn't it 30 divided by the square root of 25, which would equal 6?
Perfecto. Thank you very much. See, participate. That's exactly what it is. Remember, the central limit theorem tells you sigma sub x bar is equal to sigma divided by square root of n, right? Thank you, George. But sigma is 30, right? Square root of n is the sample size, which is 25, square root of 25. So 30 over square root of 25 is 5, which is 6. So sigma sub x bar is 6. Sigma sub x bar is 6. Now, there is one comparison I want to make here before I forget. Look at the population distribution. It has a standard deviation of 30. Look at the sampling distribution. It has a standard deviation of 6. That means this one is smaller and this one is bigger, which means that the population is spread out more. Like if you look at the left side diagram, with respect to the mean, with respect to the middle, right here, the population data points are spread out further, whereas with respect to the mean here, which is also 50, the numbers in the sampling distribution or the averages in the sampling distribution are very close to each other. And if I were to look, if I were to change this number, who said it has to be 25? Can I do it 100? Yeah, sure, I can do it 100. So if I do it 100, if my n is 100, look, is gonna be sigma sub x bar is equal to sigma over square root of n, that is 30 over square root of 100, which is 30 over 10, which is just 3, right? So then if I increase the sample size, it's gonna become even more narrower, like that, okay? So if you want to increase the accuracy, if you want to get closer and closer to this population mean, you just have to increase the sample size, which conforms with your common sense. If you want to get a better approximation of something, you increase the sample size. Let's say if I ask, I don't know, somebody named Alondra who didn't talk, and I ask her, hey, Alondra, go and find the average grade point for Hartnell College. She goes out and asks 2 people, okay? Hey, what's your grade point? What's your grade point? And she gets 2 numbers and she adds them up, divide them by 2. And she comes back to me and saying that this is the average for Hartnell College. And then on the other hand, I asked George to do the same thing. He went out and asked 100 people or 100 students, and he got 100 numbers and he added them up and divided by 100, and he gave me that number. Which one of these numbers you think would be more reliable? Obviously, George's number, right? Obviously, George's number. Now, I don't mean to be saying one thing or the other. I could easily have Alondra collect 100 data points and George collect 2 data points. So just to make sure that I'm fair to everybody, okay? It doesn't matter. Let's say Alondra collected 100 data points and George collected 2 data points, okay? In that case, her average would be more acceptable or more reliable than George's average. You get the idea, right? So you increase the sample size, you get better approximation. That means you get better approximation or get more and more closer to the true average of the population. And that's what it is. So guys, this topic is a little bit harder and I want you to participate. Don't be shy, okay? It's much better to try something and fail than not to try. It's given, okay? It's always better to try something than not trying. You can try and not everybody is going to be successful, okay? Most of us will fail. But at the end of your life, one thing you will regret towards the end of your life, and it comes from real data. Many people who are very close to death, like in their late 80s, 90s, or close to 100, living in care home, anytime they could expire, they could die. They were asked this question: what is the biggest regret you had? It's not by the way, I didn't drive that car, expensive car, or I didn't buy that nice home or whatnot. Many of them, not all of them, many of them, their biggest regret in life is not trying things when they had the opportunity. Like you wanted to go out and see the world, okay? And you don't try it. You didn't even try. You said, oh my gosh, I'm so busy right now, I can't do it. I'm gonna do it next year. Oh no, I gotta wait 5 years. I gotta buy this nice home and build up my career before I do that. Then you wait another 5 years. And in no time, you figure it out that it's too late. And in no time, your responsibilities grow so much that you never make it. At the end of the day, it's not about success so much. It's about trying things and having fun and making mistakes all the time. Failure is a welcoming thing. Okay, failure is a wonderful thing because you learn so much from it. And if you keep trying, you will be successful. All right, so participate, okay? Clear up. Next, I did this one, and okay. Now the next one, everybody, you need to participate here as well. Get your normal distribution table up, everyone. Normal distribution table up, and I'm going to ask you to do some calculations here. Find the probability that a randomly selected person spends more than 120 minutes on the social media. So now a randomly selected person, that means your n is equal to 1. You have to kind of figure it out from the wording of the problem. A randomly selected person. So remember, your mean was 50, right? Mu is equal to 50, and your sigma was 30. So when you are trying to find the probability that a randomly selected person, X, okay, is greater than 120, that a randomly selected person's time spent on social media is greater than 120, right? So 50 is here right in the middle, 120 is going to be right here, and greater than means you're looking for this area. Now you should remember that those 2 weeks that I spent, by the way, on normal distribution and going back and forth between any normal distribution and standard normal distribution, those things are going to come handy right now. So now what we are going to do, we are going to convert this into standard normal distribution that has a mean of 0 and standard deviation of 1, mean of 0 and standard deviation of 1. So it's going to be corresponding to some z value here. So this x value, this is the x, maps to the z value there. And we know how to find it. Z is equal to x minus mu over sigma, which is x is 120 minus mu is 50, right? Mean 50 divided by sigma is 30. So that's 70 over 30, which is 7 over 3. But z is equal to 2.33 approximately. So this is 2.33. So in essence, I'm looking for the area to the right here. All right, probability of x greater than 120 is the same as the probability of z greater than 2.33. Probability of x greater than 120 is the same as z greater than 2.33. Now, If you look at the standard normal distribution for 2.33, standard normal distribution table for z-value of 2.33, it is not going to give you the area to the right, but rather it is going to give you area to the left. But I don't want the area to the left. I want the area to the right. How do I find the area to the right? Again, volunteer. How do I find the area to the right? Anybody?
You subtract the z-score that you got from 1.
Exactly. Thank you, Jessica. And Dennis both. So it's going to be 1 minus the probability of z less than 2.33. Okay, look at this. Look at this. All right, z less than 2.33. Now, everybody look it up in the table. For z less than 2.33, what value? What is it? What is the probability value? What do you got here? 1 minus something. What is that something? 1 minus, it should be 0.9 something.
.9901.
Thank you. Who is it?
Jessica.
Thank you, Jessica. 0.9901. So 1 minus 0.9901 is 0.0099. 0.0099, which is approximately 1%. I would say 0.99%, right? Which is approximately 1%. There is a 1% chance that a randomly selected person would spend more than 120 minutes per day on the social media. Now, I'm going to leave this and bring the screen back, and I want you to read it here. So that was this one, okay, right here, right here. Now, read this one. Find the probability that 25 randomly selected persons spend more than 120 minutes on the social media. Same thing, but this time for 25 people instead of 1. Here we are talking about 1, n is equal to 1, right? Now we are going to talk about n is equal to 25. So that means instead of considering just one person's time spent on social media, we are considering the average of 25 people. So now, n, remember, when your sample size is bigger than 1, you are dealing with sampling distribution. So now we want to find the probability that a randomly selected person, average of 25 randomly selected people is greater than 120. So probability that x, now you cannot use x anymore. X is for only one person. We are dealing with 25 people. It should be x bar is greater than 120. So look at the distinction between these two. Over there, we use the x because we are talking about one person. Over here, we talk about x bar because we are talking about 25 different people, right? For 25 people, it doesn't make sense to talk about just one x value. It has to be the average of those people's time spent. So it's going to be this. Now, there is a little bit of notation here. So let's go ahead and first draw the diagram. So this is the sampling distribution with sample size n is equal to 25 and mu sub x bar is equal to 50 because by central limit theorem, mu sub x bar is equal to mu, and we can use the central limit theorem even though sample size is less than 30 because the original population is bell-shaped. And sigma sub x bar, which we found is sigma over square root of n, right? Which is 30 over square root of 25, which is 30 over 5, which is 6. So sigma sub x bar is equal to 6. So now what we are going to do, we are going to draw again another bell-shaped curve, which has a, I don't like this bell-shaped curve. So let's draw it again. Not much better, but at least somewhat better. This is mu is equal to 0, but we call it mu sub x bar, okay? Because just to be consistent with sampling distribution, instead of sigma, we call it sigma sub x bar is equal to 1, okay? Mu sub x bar and sigma sub x bar. So we are going to use the formula z sub x bar is equal to x bar minus mu sub x bar divided by sigma sub x bar. Now, x bar is the point in question, so which is this x bar is equal to 120, right? So we are looking for the area to the right. Corresponding to this value, there will be a z sub x bar, which is right here. Only difference is this x bar thing, by the way, guys. Here we just use z and x. This is x, right? Here we use x bar and z sub x bar. So z sub x bar is equal to some value. Now, if I plug it in, so let's take it over there where we have a little bit more space. X bar is equal to z sub x bar is equal to x bar is the point in question 120, right? 120 minus mu sub x bar is 50. All of it divided by sigma sub x bar, which is, by the way, 6. So z sub x bar is equal to 70 over 6, which is 70 divided by 6 is 11.67, which is approximately 11.67. So this is 11.67. Now this. So probability of x bar greater than 120 is the same as the probability of z sub x bar greater than this value. This area and this area are the same, 11.67, which, by the way, is the same as 1 minus the probability of z sub x bar is less than 11.67. 1 minus the probability of z sub x bar is less than 11.67. So now go ahead and find it from the table, everybody. For 11.67, what do you get for z sub x bar? Did you find 11.67, everybody? If you look at the table, positive z-score, it goes up to only 3.5. 3.5. And for probability of z less than equal to 3.5 is 0.9999. And by the way, 3.5 is considered a pretty big outlier. Now 11.67 is way far out there. And I don't even know how many nines you have to put, and that's beyond off the chart. That's what it is. So this in essence becomes 1 minus 0.9999. That's for 3.5, right? I'm gonna put maybe another 4 nines. 1, 2, 3, 4. Okay. So that number is probably approximately 0.00000001, I guess. How many zeros I put? I lose track of zeros. So okay, there are 8 or 9 zeros. So the point is not the actual number in and of itself. Look, so here is the comparison I kind of wanted to make. For a single person, the probability that someone would spend more than 120 minutes is small, but still it's a reasonable number, approximately 1%, right? 0.99% is 1% approximately. But for a group of 25 people, the probability that they would spend more than 120 minutes on the social media, their average is extremely low. It's very unlikely. Why is it the case? Remember, when you're doing with sampling, when you're dealing with sampling distribution, you are narrowing the graph. That means the graph becomes, the distribution, sampling distribution becomes narrower compared to the population. See, this one is wide and this one is narrow. Remember how I told you a few minutes ago that if you increase your sample size, you can even make it even more narrower like that. Okay. So that means the chances of being far away from the mean is extremely low if you are dealing with sampling distribution. Equivalently, the chances of being closer to the mean is extremely high or more bigger. That's what it is. Chances of being far away from the mean in a sampling distribution is very, very low, or equivalently, chances of being closer to the mean is higher. All right, and that's what it is. So this topic's a little bit difficult. When I learned it for the first time myself, I was lost. I don't know about you guys. Hopefully I'm doing somewhat of a decent job so that at least you get some ideas about it. And back in the days when I took this class, we didn't have exactly video recording that you can watch later on. I just had to go and, sort of like hang around professor's office hour during his office hours, and hoping that at the very last moment he might be able to give me some time, because they're always busy. So thank God to technology. Now you can watch it multiple times and you can go ahead and try to look at the problems as many times as you want. So go ahead and look at this example if you get lost. So next is this one. So the next one, find the probability that a randomly selected person spends between 40 and 60 minutes. So that should be pretty straightforward. A randomly selected person, meaning we are talking about the population. The person spends between 40 and 60 minutes. So this is 50, this is 40, and this is 60. Now I'm gonna do this. So this is the area I'm looking for. Now, before I do anything else, I'm gonna do the same thing, but this time for sampling distribution. That's the next problem coming up. For this one, sample is 1, and now I'm asking you do the same thing for n is equal to 25. Now look, what's gonna happen for the sampling distribution, remember, is narrower, right? Because sigma sub x bar is equal to 6 versus sigma for the population is 30. So this one is narrower. So if you try to, so if this is your 50, the chances of you being between 40 and 60, which is gonna be this is gonna be a bigger area or bigger probability compared to the entire graph. Whereas this is gonna be, this shaded region is gonna be smaller compared to the entire graph, this one. All right, so that's the thing. This is just kind of like intuition that I'm trying to create. And that's why I'm drawing these two things side by side. Because this is narrower, you are more likely to be within a window of mean. Because it's wider or standard deviation bigger, you're less likely to be within a window. Okay, the same window, by the way. By that I mean same window. So 40 to 60 for one person, 40 to 60, chances of being between 40 to 60. The average of 25 people, chances of being between 40 to 60 should be higher because standard deviation is lower compared to this. So now we are going to do the same thing. We are looking for probability of 40 being less than x is less than 60. we need to convert it into Z. Now I'm not going to spend time converting to Z again because you have seen it many, many times. 0, 1, you use Z is equal to X minus mu over sigma, that formula, to this. Now, you're going to get a corresponding Z value here and Z value here. By the way, this is going to be negative 0.33 and this is going to be positive 0.33, just to give you a heads up. All right. So you're looking for this area. So it's going to be probability of negative 0.33 is less than Z is less than 0.33, which, by the way, translates to probability of Z less than 0.33, which you should know by now. I'm not going to spend time on it because I already talked about it many, many times, is less than negative 0.33. So now you need to find the probability associated with 0.33. So what is it? Somebody tell me 0.33. What value is it? I want to volunteer. What value is it for 0.33?
0.6293.
0.6293. 0.6293. Good. Another volunteer for negative 0.33.
Is it 0.3? Is 0.3707?
Exactly. 0.3707. 3707. Thank you. So 0.6923, 0.6923 minus 0.3707 is 0.3216 is equal to 0.3216, which is about 32.16% chance that a randomly selected person will be spending between 40 and 60 minutes on the social media. So this probability is this number. So the probability that a randomly selected person spends between 40 and 60 minutes is roughly about 32%. Now this one should be higher. So let's go ahead and do this. So we are going to have to draw the corresponding, right? This is mu sub x bar is equal to 0 and sigma sub x bar is equal to 1 for this distribution. And this is z sub x bar. Oops. This is z sub x bar and this is z sub x bar. One is positive, one is negative. And if you do the math here, you're going to get, so probability of 40 less than x bar is less than 60, which is probability of z sub x bar between what? So let me just do one calculation here. Z sub x bar is equal to x bar minus mu sub x bar over sigma sub x bar, or z sub x bar is equal to x bar is the point in question, 40, minus mu sub x bar is 50, divided by sigma sub x bar is 6, right? Yeah, 6, which is going to be negative 10 over 6, which is going to give you z sub x bar is equal to negative 1.67 approximately. Negative 1.66. So 10 divided by 6 is negative 1, yeah, 1.67 approximately. So this is going to be negative 1.67, and obviously this is going to be positive 1.67. So this is going to be negative 1.67 is less than z sub x bar is less than 1.67. Now, which is the same as probability of z sub x bar less than 1.67 minus the probability of z sub x bar is less than negative 1.67. Now go ahead and find these values, everybody. For 1.67, what is it? Somebody else, other than the two people responded last time. I want a new volunteer. For z sub x bar 1.67, what is it? Jessica, Laura, what is it? Jessica, Laura, are you here? 0.9999, that is incorrect. Anybody else? .0475, that's for the negative one probably. Negative 1.67, negative 1.67, yes, you're right. That's for the negative one, sure. So for this one, somebody got it, negative 0.0475 for this one. And then what is for this one? Somebody else. Guys, you guys should be very comfortable with it and proactively answering this. 1.67, what is it gonna be? If you cannot do this problem, you are kind of not ready. Let's put it that way. Thank you, George. 0.9525. 0.9525. 1.67, 0.9525, yes. So 0.9525 minus 0.0475 is 0.905 is equal to 0.905, or it is 90.5% chance. Now look, for the sampling distribution with sample size 25, the probability that someone spends between 40 and 60 minutes on the social media, or average of 25 people falls between 40 and 60 minutes, is way higher than for one person. For one person, there was a 32% chance that, about 32% chance that it would fall between 40 and 60. But for average of 25 people, there is a 90% chance that it would fall between 40 and 60. You can see how high the probability is. And this is a consequence of the central limit theorem. And this is very powerful. This allows us to find the mean, or in some cases, standard deviation of the original population, get a very good understanding or good range for the mean and the standard deviation of the original population. So it's very, very important for you guys to understand these concepts. Any question, anybody? All right, I think, oh, sorry. Any question, anybody, once more, before I move on? Okay.
No.
Yes.
No, it just took me a second to realize that how to plug in the chart.
Okay.
Yeah, just had a refresher. Thanks.
Okay, good. All right. I think this is enough information for the day. This is a bit of a heavy loaded class. So go ahead and work on the next problem next time. So today, tonight, tomorrow, okay? Work on the second problem, Mr. Zach, the founder of Facebook. Exact same problem, I just changed the numbers a little bit, okay? And then I will do both of these problems on Wednesday, but in between, I want you to absorb the material so that you can get a better understanding of those problems, okay? So please go ahead and watch the video and make sure that you are clear on the concepts. All right. Thank you very much. Have a wonderful day. I'll talk to you on Wednesday. Thank you. Have a good day.
Thank you.
Thank you.
Thank you.